deploying and debugging HTTP3 and other cautionary tales. I have a few anecdotes for you today, but I'm going to start off with one of my favorite jokes. It's about Snow White and the Seven Dwarfs, the Disney version where the dwarfs have funny names like Dopey or Sneezy. Not many people know this, but there actually used to be about 100 dwarfs, but they started disappearing one by one until there were only 8 left. It was only then that they started to suspect one of their own, a dwarf called Hungry. Now, I love this joke because it has everything, right? The twist at the end, the play on words, cannibalism, all the things that I like. But the best thing is, it makes you wonder, what happened to Hungry? Did the dwarf send one of their own to deal with the problem? Is that how Grumpy became Grumpy? Or maybe Dopey is the lobotomized version of Hungry, who knows? It makes you think. Now, the point I'm trying to make is, in a complex distributed system, like dwarven society, having a single bad egg can easily take down quite a bit of the rest as well. This is what happened to Google when they DDoSed themselves with their QUIC implementation. To understand this, we need a little bit of context. So imagine you have a client connecting to a server and they need to authenticate with username and password. And it's useful that both the client and the server will remember that for the next time. So that the next time the client connects to that server, they don't need to do that again. They can just keep on going. This is a common occurrence, many different use cases. What was at play here was something called TLS session resumption. Now, in this case, you don't actually want the server to really store that state for all the individual clients, because then you suddenly have huge distributed storage issues. So what they do is actually a clever trick. The server is going to take the state they want to remember, put it in a blob, and encrypt that blob using a private key, so only the servers can read it. They then give this blob, this token, to the client. The client acts as a storage device for the servers. When the client tries to reconnect, they just send along the encrypted token. If the server can successfully decrypt it, it means it wasn't tampered, and so it's good state, and we can reuse it. Many different ways that this is being used. Simplifies things. You only need one shared private key across the service. This is far from simple, as some people might know, but still, it's doable. Now, knowing this, imagine that you're trying to deploy a new version of the code. But tokens generated by this new version will instantly crash older versions of the code. What happens? So let's explore this. So basically, they had a new version. They want to deploy it. As best practices go, they do a canary deployment, right? Only a few servers actually have this. Clients start connecting, and they are getting this contaminated token, let's say. Let's call it Hungry, right? This is all fine. The new code works with this. But after a while, the client might need another connection to these services. It's very unlikely that the client hits the same canary deployment again, because it's very small. So what mostly happens is the client will actually hit one of the old servers, which instantly crashes. It can't deal with the Hungry, okay? That's bad. What makes it worse is that the client says, oh, that's weird. I wanted to get a connection, and I'm hearing nothing back. Maybe, it was just some packet loss. Let's try again. Let's bring down another server. Client doesn't hear anything again. What does it do? It tries again. Now, luckily the client, Google Chrome in this case, did have some kind of an exponential backoff built in, so it's not quite as bad. But still, every infected client could take down over a dozen backend servers just by itself. And Google says that about 10% of its entire fleet went down. And that might seem manageable, but it was highly localized to some countries in Europe. And so in those countries, Google was effectively just completely down. Now, interestingly, think to yourself, if you would have this situation, what would you do to mitigate it? Right? You have a canary deployment, suddenly everything goes red. What do? You roll back. Doesn't actually help in this case. It kind of no longer makes it worse, so it kind of stops making it worse, but it doesn't actually solve the problem because the state is already at the clients. As long as the clients keep on reusing the Hungries, you will have a few bad hours or even days. Ironically, deploying the new code to 100% would have helped, but that's not exactly something you want to hear in this situation. So the actual solution was to send in Grumpy, right? The big red button, they call it. They disabled QUIC across their entire fleet for a couple of days, waiting for the tokens to expire. Now, all of this comes from a different talk from someone at Google. They describe this as a new type of bug, a contagion bug, where you have contaminated state at the client, which you, of course, can't purge. And so you need new ways of dealing with this. I highly recommend you go and watch that talk as well. It has many other details and also some good SRE insights there as well. But I need to go on to my next anecdote, which was a recent problem we had at Akamai, which was that customers were complaining that they got 403 forbidden errors, firewall was complaining they were trying to use HTTP 3. This happened on domains where HTTP 3 was disabled. So very weird. How can that happen? Well, let's explore. Let's imagine we have a website, SRE.com, with two subdomains, the www for the main site, and then the static for images, JavaScript, CSS, typical setup, right? Now, in this case, you would have two different connections. Browser would have two different connections to the different subdomains. Now, in real-life deployments, it looks somewhat different. You don't actually have two individual servers on the right. You usually have just one server or one endpoint that can serve assets for both subdomains, right? Whether this is a CDN edge server or a reverse proxy, usually that one thing you connect to can actually serve for both of the subdomains. In that case, it's kind of wasteful to open two separate connections, right? You could just reuse one connection and simply get the stuff from there as well. And this is exactly what happens. This is something called connection coalescing or connection reuse. If the client is quite sure that the request will end up at the same machine or the same deployment as the first, they can decide to just reuse the connection. How does it decide this? Well, one of the ways is to look at the DNS. If they resolve to the same IP, that's a good signal, but it's actually not required. The main thing they look at is if these deployments share TLS certificates. So if the TLS certificate for the www is also containing the static subdomain in its subject alternate names, for example, then it will be a clear indication I can just reuse this connection. This is a good thing. It's actually good for performance, and it's common practice in all browsers today. Now, let's look at the exact setup that we actually had. So here we had the customer. They were like, HTTP3 is cool, but I'm not quite sure about the security characteristics, so I want to disable it on the www. And I'm gonna configure the firewall that it actually blocks any HTTP3 that might come in, right? HTTP3 on the static, no problem, because that's not security sensitive. Again, what you might expect to happen is this, that the browser would open two individual connections. No problem there, but you're all smart people, you can probably extrapolate and predict what happened instead. Looks a bit more like this, right? For some reason, there was already an existing HTTP3 connection to the static subdomain. Browser needed to send something to the www. Decided TLS certificate is enough for me. I don't care about protocols. And I will just send my request on the H3 connection. The firewall did its job, blocked the connection with a 403 forbidden. This is actually a bit of an oversimplification of the problem. There are many other things that need to go wrong that I don't really have time for. But the thing is, this was actually quite rare. It doesn't happen to all users, but it happened often enough that we got end users complaining, but not often enough that it was easy for us to quickly figure out what the hell was happening, right? So lots of fun. There we go. So this actually doesn't have a very simple solution. Some of our customers that had this decided to just disable HTTP3 for everything until they can disable it for everything. Some of them actually split the TLS certificates into two sets. Depending on your setup, that might be easier said than done. There is a variant of this that you can run into if you're using multiple CDNs, and they're not both enabling HTTP3. I don't have time to go into this, but if you're in this situation, maybe you should come talk to me afterwards, because this can definitely happen. Now, the third and final anecdote of this part has to do with Peter Pan, or at least the lies that Big Disney is trying to tell you about Peter Pan. They say Peter Pan is a young, gentle boy who invites other children over to his magical Neverland to come and play, where they meet other children called the Lost Boys, and they have all kinds of adventures. The only thing they need to watch out for is the villain, Captain Hook, who is clearly the bad guy because he's a pirate. Okay? This is what they want you to believe. But if you just think for yourself for a second and look past the fake news, it quickly becomes evident that in fact, Peter Pan is the real villain in this story, right? Imagine this, you have a mischievous immortal, a demigod, he's basically Loki, kidnapping kids to his secret lair. Why would he do this? Well, it's obvious. He's kind of a vampire, right? He sucks up their life energy. This is how he stays young. After a while, of course, the children grow up. He can't do this anymore. This then leads to the real meaning of the word, the Lost Boys. Now, the thing is, occasionally one of the boys is able to escape. The first one ever to escape was called James Hook. He actually lost his left hand in the process. And ever since then, James has been taking in other boys that have been able to escape and protecting them from Peter Pan. Now, I don't know about you, but I think this would make a very cool HBO series. Right? Now, the actual point I'm trying to make is that things might be different than what they appear at first, right? It depends on the interpretation. And that's what we actually had in this anecdote as well. So we had customers that were measuring performance, HTTP2 versus 3, and they got a result, but the result was not what we expected. Let's explore that. So one thing you might know about QUIC is that it improves the handshake. So on TCP, you usually need 3 round trips to get some data back on the HTTP level. On QUIC, you will then need just 2. It's one of the main improvements. And then there is this special 0 RTT thing that actually lets you do everything in 1 round trip, right? Amazing. Now, there's this company called Wix. I like to call them the GeoCities of the 2000s. They did this, they looked at the time to first byte metric, which is basically from the start of the connection to when you get the first data back. So basically the diagrams I just showed you. And they saw some nice improvements, you know, about 50% at P75, which is quite high for some countries, as we can see. Now, when I saw this, I was like, okay, that's very nice, but how are you getting the 50%? Doesn't make much sense, right? Because either you go from 3 round trips on TCP to 2, basic quick handshake, you would be 33% faster, or you would go from 3 to 1 with 0 RTT, and you were 66% faster. So how the hell did they get 50%? Anybody wants to venture a guess? Don't be shy. Louder. Half one, half, no? Good guess, but no. No one? I'm going to give you a little tip, people, for in the future. Whenever a networking person asks you what is the problem, the answer is always DNS. Right? It's always DNS, unless it's BGP. But it's always DNS. So here, it's of course also DNS. Because what happens, HTTP2 would often have a DNS overhead, HTTP3 did not. The real question is why? Why would that happen? Well, the thing is, browsers don't actually do HTTP3 on their own. If you have a new server, new domain that they haven't seen before, they won't start off with H3 because most servers don't support it. They want to be sure it's on the server before they actually try it. So the very first time you will have an HTTP2 connection, the server should then send back what is called an alt-svc header. It stands for alternative services. You're currently using the H2 service, and there is also an HTTP3 service on port 443. The browser stores this information in its cache, and after that, it will also try an HTTP3 connection, right? So this helps us make sense of what we saw. So HTTP2 will usually only be used if it is a completely new domain that we haven't seen before, which also means it's probably something we need a DNS lookup for, right? Inversely, HTTP3 is only used if we already have the alt-svc information in cache. It stands to reason that usually we also have the DNS still in cache, and so we wouldn't have the overhead. And that's how you go from 4, approximately 4, to 2 round trips, 50%. Now, is this a huge problem? No. Should you make business decisions based on performance measurements? No. But just in case you do, or you want to go with this, it's good to fix this metric and really be aware of these things. So we worked with Wix to remove the DNS from the data, and then you get a much more predictable, approximately 33%, indicating they were actually not using 0 RTT at that time, right? So now it's time to ponder a little bit. We've had these 3 anecdotes, relatively complex issues. I don't know if you agree, but I would call them not the most trivial things you've probably seen today. They require a relatively in-depth knowledge of how these protocols work. That's 1. And 2, they also require quite a bit of insight into, 2, they actually have several steps, you know? You need several things to go wrong in sequence, often across different protocols to end up at the failure state. So the thing is, what I believe is that we need more observability tools for the lower layers of the networking stack, right? You probably have some kind of tracing solution where you can trace the full request from clients to the backend and then all the way back, but it usually stops at right beneath the HTTP layer, right? Or not even that. I would argue you need something more beneath that to be able to quickly dissect this kind of issue with these complex protocols. This is kind of the conclusion that I had about 6 years ago, which led to something called qlog and qvis, which I'm going to give you a bit of historical context on now. So 2018, I was doing a PhD, and this was when the QUIC implementations were just getting started, right? So people were really having to debug and really having to figure out what they were doing wrong. And I wanted to, as part of my research, help with this effort, find some bugs. And one of the things is that I am a very visual thinker. I really want to have these kind of diagrams or interactive tools with nice colors that help me interpret what's going on, like a sequence diagram that shows you which packets are going from the client to the server and back and what's actually in those diagrams. Now, when I wanted to make such tools, I, of course, first had to get data to visualize with them, right? And now you might be thinking, well, Robin, not a problem. Why don't you just use Wireshark, right? You can get the data from the PCAPs. Wireshark visualizes things in a certain way. Why can't you do that? Well, you can do this to some extent, but you would also always need the decryption keys. QUIC is so heavily encrypted that you can't really do much useful without the keys. And in some, especially production systems, you will not always have these keys. Second thing is that Wireshark is not always fully up to date with the latest features. Like Lucas also mentioned, they only had full HTTP3 decryption just a couple of weeks ago, right? This is not a dig on the Wireshark team. This is more a testament to how complex these protocols are. Let me be very clear, Wireshark is one of the best open source tools we have, right? They're great. But even if everything works, if you try to convert a PCAP or a dissected PCAP to JSON or XML, you quickly run into challenges, I would say, in a nice way. I could rant about that for days. I will not. But so that kind of works, but it's not optimal. And even if that would work, you would still have some things that are not in the PCAP, right? Internal state. Things like what the congestion controller is doing and why it's doing what it's doing are simply not reflected in the wire image. So especially for debugging, you would miss out on a lot of useful stuff there as well. So all of these things culminated in us looking at, can't we find other sources of data? So the first thing we tried was to look at the raw command line logs of the QUIC implementations that were going on there, which was a lot of fun because all application developers are very consistent. So a nice example on the top right, we have RECV, which means receive. We have RX, which also means receive. And then we have RCV, which predictably means recovery. Yeah. So we did this for about 4 implementations. We got really tired of that. And we were like, yo, wouldn't it be nice if they all would just output the same format? And wouldn't it be nice if it would also just be nicely parsable, you know, maybe something like JSON that would make our tooling work much better. So what we did, we wrote a nice paper, an academic paper on this, proposing this, going to present it at a conference, really with no hopes at all for people actually listening to us, because, you know, there is us, young PhD students, telling companies like Facebook what to do, right? That's never going to happen. Long story short, I'm very happy I was wrong about that, because nowadays over 70% of all QUIC implementations have some form of qlog support, right? And Facebook is actually using this in production as part of their observability stack, proving that it can actually work at scale there as well. And we are currently in the process of standardizing the qlog format in the IETF as well. Ironically, one of the very few deployments that does not have qlog support is my employer, Akamai. Funny how that works. But so, with this, we were blown away that people would actually want to do this, but it was very good because suddenly we could get qlogs from all these high-profile implementations and help them debug their issues. So we actually have a very extensive suite of tools called qvis, which are even web-based. You can just upload the JSONs, which sometimes gives some very fun things. So this is a sequence diagram. These big green things are actually acknowledgement frames. So in QUIC, everything is a selective acknowledgement, and it's not bounded. You can have as many acknowledgement ranges as you want. And if you have an implementation that doesn't actually prune the ranges after a while, or you have a lot of packet loss, like in this case, these can actually get pretty big, which you can immediately see in the visualization. Another fun diagram is to help debug congestion control. So this here, the purple line is actually the congestion window as seen by the application. This is something that is not on the wire. You can't get this from a PCAP. But of course, because we're doing application logging, we can get that. And you can very nicely see a nice new Reno sawtooth pattern where the congestion window grows. And then the RTT, this is actually the measured RTT as seen by the application, not derived from the PCAP, what the application is actually using. You can see how that goes up and down as the buffers fill and drain with the congestion control implementation. And then we also have a very nice cubic version of that. Now, I think most of you probably don't care about this at all, but the few people who are here that do worry about congestion, I hope you're going like, yay, you know, because this is something that's, correct me if I'm wrong, typically quite difficult to get for a production level TCP stack. There are several other tools there as well, but I don't want to spend too much time on this. This is not supposed to be a QVIS tutorial. I have other talks that you can watch for that. I also don't want to pretend like qlog and QVIS are like the best thing since sliced bread. They don't solve everything. They have some shortcomings. But I do think they're very good for what they were initially intended for, which is helping to debug implementations that are not completely ready yet, or to debug these very deep protocol level issues. I also think they can be a basis for indeed what I said, like an observability system that goes much deeper than what you might currently have, looking into the depths of these stacks, correlating this with the higher level data there as well. So that's definitely something I think you should consider, or companies that offer observability solutions should consider. Offer solutions that incorporate this kind of thing. Doesn't have to be qlog, but some kind of endpoint logging would be nice. That being said, I think most of you here can probably, in your day-to-day jobs, get away with just using Wireshark, right? Especially since that last update a couple of weeks ago, it's now pretty full-featured. And so the next thing that I want to show, the next anecdote, is basically one of the issues that I debugged a couple of weeks ago using Wireshark. This, of course, has to do with Cinderella, who went to the ball, had to leave at midnight, and left behind her glass slipper. The prince then goes on a tour across the kingdom with the slipper, because, of course, the single girl that fits the slipper will get to marry him. Of course, the evil stepsisters from Cinderella try to make the slipper fit their own feet. In the Disney version, this is done in a sort of comical fashion, I would say, as you can see. But the original, darker version has one of the stepsisters taking a knife and start cutting to try and fit there. It's quite gruesome. Why am I showing you this? Because this idea of having something that's a bit too large, trying to fit it into a smaller container, that's actually something we also have in QUIC. So we had a customer, like some customers see better improvements than you expect. Some of them complain that they don't see any improvements at all. Okay, so how can this happen? Well, this is what I explained before. This is what should happen. This is the theory. What actually seems to happen in practice for some customers is a bit more like this. You actually have an additional round trip of handshake overhead in the QUIC handshake. The question is, how is this possible? This has to do with something called the UDP amplification attack, where if the attacker is spoofing the IP of their victim, they're trying to bring their victim down with a large DDoS, instead of using their own bandwidth directly towards the victim, what they can do is, in this case, for example, send a DNS query over UDP. And if the server then responds to the spoofed victim IP with a much larger response than the request was, then you get what is called an amplification. So the attacker is able to get much more bandwidth than what they actually put in. Now this is quite trivial, it's only 5x amplification, but there have been situations where you have thousands x, like the mem crashed, link below, and that's kind of a big problem in practice. So this is only if you have UDP, because you don't have a handshake, but guess what? QUIC runs on top of UDP, and it's vulnerable to this during the handshake. This is kind of trivial to see if you consider zero RTT, because there you actually have a full request in the very first round trip, and if the server would then just, let's respond with the entire file, let's just say, you would easily get a very large amplification factor out of there. So one of the ways that QUIC, the spec, tries to deal with this is it says QUIC servers can only have an amplification factor of 3. So however much data the client sends, you can only respond with 3 times that amount of data before the server has to wait till they get something back from the client to make sure the IP was not spoofed. This probably makes sense in the context of zero RTT. This also happens during the normal QUIC handshake. This is because during that very first round trip, you need to send the full TLS certificate. Some of these certificates can get relatively large. They can get larger than that 3x limit, and so you get into the issues that we said before. You can't do a 1 RTT QUIC handshake, you need to fall back to 2, because you have a leftover part of the certificate that you can't send until you're sure the IP is not spoofed. So I know about this issue, and so when the customer came to us complaining, I was like, okay, maybe it's that. I need to verify that it's that, so I'm going to try and verify that using wireshark, right? For this, I just wanted to have a request to the server. I was going to use curl. Curl has good HTTP3 support, but it's not compiled in by default. You have to compile it yourself. So I have like a reusable Docker image that you might want to use for that. This Docker image also contains full qlog and decrypted PCAP support as well. I'm not going to go through the code. This is for if you look up the slides later. Just go to the GitHub repository there. But basically, I just ran curl. I got a PCAP back. And let's look at what was in there. So the connection starts, like Lucas said, with an initial from the client, which has the client hello and the TLS. That's all very nice. Just one packet. Client sets one packet of about 1,240 bytes. The next 3 packets then come from the Akamai server, which can only send 3 packets, right? Because it's limited by the 3x amplification limit. Then it needs to wait until that next packet, which is coming from the client and which is an acknowledgement. So the client acknowledges, I got your 3 packets. This is a clear indication to the server, this is not an attacker spoofing an IP, because the client is actually answering. So now I can start sending more data. The next 2 packets then is the remainder of the data. By then, Wireshark is indeed able to decrypt the entire TLS handshake. And we see that the certificate here is ever so slightly larger than the 3x limit, right? Now this is just a certificate. There's also other QUIC overhead, so it never would have fit anyway. But like, it's a very small difference. It causes us to have a full round trip of overhead there as well. And so you incur an additional round trip just because of that. So it's very easy to debug that kind of thing with Wireshark. That's good. What you might also notice here is that there are lots of magic numbers at play. So curl uses an initial packet size of 1,240. Not all clients do that. I think Google Chrome is about 1,300 or 1,350. So if you have this issue, it actually depends on which client you're using. Nice and deterministic. And then if you would compare this, because our customers do that, right? They compare Akamai to competitors. You will see some of our competitors don't actually have this problem. They don't adhere to the 3x limit. They will happily go to 4x, 5x, 6x, just to fit everything inside that first round trip. This is not allowed by the spec, people might say. If you actually talk to IETF people, it becomes quickly clear that even they don't remember where the 3x actually comes from. It's not really a verified thing that, like, if you go over, you will bring down the internet. But still, it's like a very explicit performance versus security trade-off that is being made by the implementation. And so, depending on this kind of configuration, you might get very different performance statistics and behaviors from your QUIC stack, even though they are the same protocol, right? So another thing to keep in mind. With that, I've come to the last big part of the presentation, which is about the Lion King. So in the Lion King, everything is nice and dandy as long as Mufasa was the king, right? But of course, he has a brother Scar, and Scar says, you know what? Whatever Mufasa is doing, I bet I can do that better. So he hatches a complicated scheme. He actually murders his brother and takes over the kingdom. Now, of course, very predictably, it turns out that Scar actually can't do things better than his brother. Actually messes it up quite tremendously. And he is quickly dethroned by his nephew, Simba, right? Now, the nice thing about The Lion King is that I don't actually need to find like a dark version of the story. The Lion King is dark enough by itself. I mean, Disney, how dare you? I was 10 years old, okay? Now, what I'm trying to say, this is a common occurrence. Like someone looks at something and says, you know what? I could do that better. Of course, often being proven wrong. So with that in mind, let's talk about deploying your own HTTP3 stack. Which is quite possible. There are actually quite mature open source implementations, including some from Cloudflare, Fastly, Facebook. With a few caveats, they don't often open source everything you need. And most of the things they open source are not fully configured for production level performance or security. So you can't just take a vanilla stack from GitHub and start deploying that. You need to do a bit more, and for that, of course, you need a lot of knowledge about what the protocols are supposed to do. A lot of the off-the-shelf servers, let's say Nginx or Apache, either have immature support, I would say, or have no support at all at this point. So it's kind of touch and go. This is all made worse by what I would call the OpenSSL controversy. Basically, OpenSSL is being hostile towards the QUIC community. In my opinion, they refuse to implement the APIs that everybody else is using. And so the only option you have is to use a different TLS library if you really want to do this at production level, which depending on your setup may or may not be a big problem, right? But believe it or not, all of this is actually the easy part. It gets more complex because, you know, just running an H3 server, that's doable. But then you need to load balance it. You need to firewall it. You need to do key management, and you need to set up DNS. So I'm going to just look at just one example, just one quick feature that impacts a lot of these things, which is called connection migration. So in TCP, a connection is defined by the for tuple. If something of that changes, say the client goes from Wi-Fi to 4G, or you have a NAT rebinding, the TCP connection breaks and needs to be reestablished. This is annoying because you also need to reestablish the TLS session and that kind of stuff. It's inefficient. So what QUIC says, okay, let's solve this with connection migration. Very simple. We're just going to assign each connection a unique ID. It's basically just a random number. And even if the for tuple changes, as long as the ID stays the same, we don't need to set up a new connection. We can just keep on reusing the old one. Very simple. We're just going to put that connection ID in every single QUIC packet header that we send, right? Works nicely. You need a few changes in your deployment, especially if you're using stateless load balancing. So these things usually use a hash of the for tuple to have a stable mapping to the backend servers. Of course, now the for tuple can change, but if you just update your load balancer to just look at the connection ID instead, everything should be just fine. Right, conceptually. In practice, if you would do it like this, you would be creating a terrifying privacy problem, because you would have a single persistent tracking ID that will follow the user around along different geographical networks, which a lot of nation states would thank you if you would actually deploy this, right? So this is not actually what happens. This is not actually what QUIC does. QUIC is aware of this. The solution to this is actually have multiple connection IDs that map to the same connection. So you start off with just one. Once the connection is set up, the client and server are going to exchange additional connection IDs in the encrypted channel. So multiple IDs mapping to the same connection. If the client then switches networks, it will also just switch the connection ID, leaving all the monster in the middle attacks without something to track. Conceptually, because of course now our load balancer is broken again, because there is nothing stable to use the routing for. Then another clever trick. The insight is that the connection ID is just a random number. So why not just use, like, let's say the first 4 bytes of the connection ID. Let's put the server, the backend server ID, in those 4 bytes. And the stateless load balancer just needs to look at those 4 bytes, and it knows where to send the thing off. And the rest of the connection ID can just say random stuff. And you can go very far in this. You can also put other stuff in the connection ID. For example, Facebook has been using this for zero downtime switches of their code base. They run multiple processes, one old, one new, and they encode which process this thing should be sent to in the connection ID. So very flexible, relatively easy to implement until you start thinking about this. Because who actually chooses the connection ID? It's the client. Because the client initiates the connection. Right? The client has no idea where it should be load balanced to. That's something that the deployment decides. So this can't actually work. And now we get to the actual final design that's actually in QUIC, where you actually have a split CID setup. So the client has its own set of connection IDs, and then the server chooses its own as well. So different CIDs in different different directions. This is why, like Lucas also said, like in the handshake packets, you will see something like the destination connection ID and the source connection ID. That's because they both have their own different connection IDs going up. You might think, oh, finally, we're done. Robin, stop talking. Not yet. This all sounds nice, you know. Let's encode detailed information about our backend infrastructure in publicly available data. What could go wrong, right? Well, they might start to DDoS one specific server because they know exactly which ID to target, right? So again, a lot of ways to deal with this. The way that, the proper way, I would say, or the one that's also being worked on in the IETF, is to just encrypt the connection ID there as well, so that only the load balancer and the backend servers can actually see what's in there. Which kind of works, but now suddenly you need to share a new key between your stateless load balancer and all the backend servers, right? So I could keep going. This is not even the final form, but let's stop. And this is just one example, right? Just one feature. There are many others that might not be quite as complex, but still have several issues. You now also understand why most deployments don't actually support connection migration at this time. Yes, what I wanted to say is that, just a couple more minutes, please. What I wanted to say is is so complex, but I really wouldn't like a world where only the big CDNs or only the big clouds are able to deploy an HTTP3 stack, right? That would be terrible in my opinion. So what I've been doing is trying to set this up myself and trying to find out where the pain points are so I can maybe help some of you in the future. I'm doing this on Akamai's own cloud platform. As you may know, we recently acquired Linode. So we now also do AWS and Azure, but then as part of the Akamai platform. And one of the cool things I think that I've been doing is that I have like, my deployment has an HTTP test page, an HTML test page. If you go to that, you can actually click a button, get me the qlog, and it will grab the qlog of the current connection from the servers and give you that inside of the browser, so you can easily copy paste this into qvis, for example, very easy to debug. So what I'm trying to say is if you're interested in setting up your own stack, you might want to consider Akamai and our cloud services. After that obvious marketing ploy, it's time for the conclusion. I hope I've said many interesting things to you today that you can take home, but the one thing I hope that you remember, the one thing I hope that you will do after this talk is tell the hungry jokes to everyone. This needs to be proliferated much more. One thing I'm afraid of after this talk is that you are afraid of HTTP3 and QUIC. That you're like, oh, this is way too complex. You know, this is not something I ever want to do myself. And I would find that, you know, that would be a shame, right? I don't want to have this. I think really, in essence, yes, these new protocols are complex. That is true, but are they really more complex than what you currently have in your TCP stack? I'm not sure about that. Maybe a little bit. Mainly, I think they're just different. There's just a couple of new different concepts. Once you learn them, it should be quite feasible. I would just say, don't throw yourself into the deep end. Get yourself started slowly. And luckily, I have a lot of additional content out there on the internet that help you to do exactly that. And of course, come find me if you have any more questions. Thank you all so much for your attention, and hope to see you on the floor.